In this video, I'm going to be talking to you about linear independence. But before I tell you what linear independence is, I need to tell you something really important. And that's that solving the system AX equals B is equivalent to finding a combination of the columns of A that adds up to B. And let me just show you using a system of equations that we have already solved in this class, how this works. All right, so this is a 4x4 system that we've worked with at some point in the class. I'm not really sure when. I just kind of asked when I was giving lecture. I was just like, hey, somebody give me a system that we solved and had a unique solution. So we row reduced this. That x1 was 3, x2 was 1, x3 was -1, and x4 is 2. But what I'm proposing is the vector 5, 5, 17, 21 can be written as 3 of the first column plus 1 of the second column plus -1 of the third column plus 2 of the fourth column. And let's just actually distribute those numbers and convince. All right, so I'll let you check for yourself, but I think the one that's most surprising would be maybe the 17 and the 21. Well, that 17 is 3 plus 2 is 5, minus 4 is 1, plus 16 is 17. And for the 21, I've got 0 plus 1 plus 20. Okay? And you can check to see that the other two work, and they do. And so this is just a kind of a different way of thinking about solving systems, and a different way of thinking about the matrices that we've been working with so far. Okay, so now let's talk about linear independence. And we're going to say that a set of vectors is linearly independent if the only way that we can, hold on, I know that's not, if the only way that we can combine the vectors v1, v2, v3 all the way to vn, a number of each of them, and get back the zero vector is by taking 0 of each of them. And I think that, actually easier to understand linear independence by looking at some examples than looking at the definition. So for example, here I've got myself a set of 3 vectors, u1, u2, and u3. And I want you to just kind of look at u3 and realize that u3 is equal to 2u1 plus u2, right? -4 plus 5 and 6 plus 4. Okay, 2u1 plus u2 equals u3. So I'm going to write down that equation right here. So 2u1 plus u2 equals u3. Okay. And now what I'm going to do is I'm going to subtract u3 from both sides of this equation. Okay, so I'm going to have 2u1 plus u2 minus u3 equals the 0 vector, right? Because it wouldn't make sense for me to say it equals 0 because on the left I've got, a total of some vectors. So it needs to be a vector that I get on the right side. So it's going to be the 0 vector. But I have myself a non-trivial solution to the equation that I'm about to highlight in gray right here. Oh no. Hopefully that will go, yep, behind it. So I have myself a solution to the equation highlighted in gray that is not just each of the vectors, meaning that I'm going to conclude that the set S is linearly dependent. And because I exhibited a non-trivial solution to the equation where I'm getting a combination of the vectors and getting 0 back. Okay, so let's get one that is linear independent. Okay, so I just brought back the matrix from the beginning of our discussion, and I'm just going to ask you, are the columns of M, which are a set of 4 vectors in R4, is that set linear independent? And what we're going to need to do is we're going to need to solve the equation in gray. Is there some number of the first column of M, which I'll just call M1, some other number of the second column of M, some third number of the third column, and some fourth number of the fourth column of M that I could add all together and get the 0 vector back? That's kind of the question that I'm asking when I'm asking, are they linear independent or not? So what we could do is, remember what I told you at the beginning, the important message was that finding a combination of the columns to equal 0 is going to be the same as augmenting this original matrix with 0 and row reducing, right? Just solving the system. And so this is part of the reason why I told you in the last video that we were going to be really interested in solving homogeneous systems, because determining if a set of vectors is linear independent is equivalent to solving a homogeneous system. Now, I'll just go back and look. We had a unique solution for the system that had kind of the same coefficient matrix. So I know that the row reduction steps are going to go the same way on the left side, but on the right side, over here on this last column, I'm just going to have a bunch of zeros at the end because I'm just going to have a bunch of zeros added together. So I know that on the left side, it's going to row reduce the same way. Without boring you with all the row reduction steps. And then I'm going to end up over here. But what this means is that the only way that I can, add up all of these things to equal 0 is by taking 0 of the first column plus 0 of the second column plus 0 of the third column plus 0 of the fourth column, which is exactly what it means for, the set of columns of M to be linear independent. So I would answer this question with a solid yes. So one relevant theorem I want to tell you about is that if we have a set of vectors that are m-dimensional, but we have, say, more vectors than we have dimension, then we're going to automatically have a linearly dependent set. Okay, so I think I'm going to illustrate it for you once with a concrete example, and then I'll talk about it in general. So look at, for example, look at the set 1, 0, 0, 0, 1, 0, and wait, hold on. This is not the right example I'm copying. Yeah, I definitely wanted this example where I had 3 two-dimensional vectors and we saw that they were linear dependent because I just kind of cooked them up so that u3 was 2u1 plus u2. But I'm just going to show you how this is going to be true in general, just because I have too many two-dimensional vectors in order for them to be independent. So what I would do if I wanted to check this is I would kind of push them together into a matrix. So I might put, -2, 3, 5, 4, and 1, 10 into a matrix, augment it with 0, 0, because I want to find out a combination of these columns that add up to 0, 0, and I'm going to row reduce. Okay, this is going to be not the easiest row reduction ever because I just made these numbers up, off the top of my head. So what I'm going to do is I'm going to multiply row 1 by 3, so I'll have -6, 15, 3, and 0, and then I'm going to multiply row 2 by 2, 6, 8, 20, and 0. Okay, now I'm going to go over here and add down, so I'll have, what am I going to have? 0, 23, 23, and 0. Seems almost too good to be true, which I'm going to then divide that row by 23 and get 1, 1. Oh, oops, lost my vertical bar. All right, so I'll have 1 and 1, and then I will have the vertical bar there. And then, if I was to go and, let's see, yeah, I'm going to have to divide this by -6, so that'll be 1. 15 divided by -6, I don't really even care. I'm sure that's reducible because they both have a factor of 3. 3 divided by -6 will be -1/2. Okay, so what is -15 divided by 6? That's -2.5, and so maybe I'll just write that also as a decimal, and then I'll fill in 0 there. All right, but I could add 2.5 of row 2 up to row 1 to kill off that -2.5, and then I would be in reduced echelon form. Okay, so I'd have 0. I added 2.5 of row 3 to row 1, so I have 2.5 minus 1/2 is going to be 2. Okay, and that 2 and 1, that's not a coincidence, right? Okay, but we'll probably look at more at that later. Okay, so we're seeing that we have a consistent system that has infinitely many solutions. Okay, which means it's not just the all zero solution, right? There are going to be other solutions like the one that we exhibited earlier. We said that what was it? U1, 2U1 plus U2 minus U3 equaled 0. But what it's going to turn out to be is that, you know, x1 plus 2x3 equals 0, and x2 plus x3 equals 0. So if we solve for these, x1 is negative 2 times x3, x2 is equal to negative x3, and x3 can be whatever it wants. But then you realize, oh, wait a second, what if I chose u3 or x3 equals 2? Then I would have, you know, kind of the combination, so that would be, let me switch up my color, I'll use red. So if I use x3 equals 2, then I would have negative 2 and positive 4, right? No, yeah, negative 4. Yeah, it's negative 2. Yeah, and so you could also see that maybe negative 4u1 minus 2u2 plus 2u3 would also equal the 0 vector. I forgot to write that as the 0 vector up here. That's kind of slow. Or write any of these things as vectors. Okay, so the point I'm making is, oh, well, to go from, you know, this equation to that equation, I just multiply both sides of the equation by negative 2, right? So there's a bunch of different combinations that can add it up to 0 if there's any non-trivial ones. Okay, and again, the trivial combination is just taking 0 of all of them. Okay? Now, in general, if n is greater than m, then let me just kind of clear out some of this noise here. Then we're going to be looking at a homogeneous system with more columns than rows. Okay? And that's the reason why this is true, why the theorem in blue up at the top of the screen is true, is that if we have more vectors than dimension, and we're determining if it's linearly dependent or linearly independent, what we're doing is we're solving a homogeneous system that has more variables than equations, which we know is automatically infinitely many solutions, which is more than just the trivial solution. Okay, I think I've said enough about that. Now, the last thing I want to tell you in this video is that any set that contains a 0 vector is automatically linear dependent. And so I want to show you why that's true, and I think you should be able to pretty easily understand why that's true. So let's talk about the set S equals 1, 0, 0 and 0, 0, 1. Okay, I'm going to start by just making it that set. This does not have the 0 vector in it, right? Okay, so I'll get to that in a second. S is going to be linear independent because there's no way I can take those two vectors and add them together and get 0, 0, 0 any way besides just taking 0 of the first one and 0 of the second one. And I think it's really easy for you to see when I write it down just like that with a really simple example. But if I went over here and added in a 0 vector, then what I could do, if I called these, you know, like W1, W2, and W3, is that I could take 0 of W1 and 0 of W2 and any number of W3 besides 0, so maybe like, I don't know, 19 W3s, and that will be 0. And the combination, you know, 0 of one, 0 of the other one, and 19 of the third is not a trivial combination. So that means I've exhibited a non-trivial combination of the vectors that gives me the 0 vector back, meaning that set is linear dependent. So any set that has a 0 vector in it will be linear dependent for the same reason, right? And I think that's all I'm going to tell you about in this video. We're going to have all sorts of consequences of, you know, linear independence, and we'll be talking about this for quite a while, but for now I was just really telling you what is linear independence. So you're going to need to work some problems, determine if some sets are linear independent or not, and then we'll be ready to move.